So it is our pleasure today to have Shuo Pang here, who will acknowledge that this meeting is indeed being recorded. And then we will get a talk on graph coloring and lower bounds for polynomial calculus and Nullstellensatz. Please, Shuo, take it away.
Thanks. So this is a long overdue talk, and it's based on the joint work with Jonas Conneryd, Susanna F, Jakob Nordström, and Kilian Risse. I would like to especially thank Jonas Conneryd for drafting parts of this talk. So our focus will be a graph coloring problem and the polynomial calculus system. Here's the graph coloring problem. You're given a graph and the number k. You're asked whether you can color the vertices of the graph using these colors without creating any monochromatic edge. And it's one of the CARP's original and B-complete problems. For instance, for this graph, you can color it by 3 colors, but you cannot color it by using 2 colors because there are triangles. And is this problem hard? Yeah, of course. Actually, it's hard even to approximate. For example, we know that if it promised that the graph is k-colorable, then current best efficient algorithm can color it only using much larger number of colors. And even if it is 3 colorable, then in worst case, it requires n to the polynomial n colors, where n is the number of vertices. And there are hardness for approximation. However, on the other hand, in practice, some class of algorithms at least sometimes appear to do well for this problem. This includes the classical backtracking search algorithm, which is like a decision-based case analysis, and integer programming, and some well-known algebraic algorithms, which will be the main topic of today. Then, given this contrast and this sometimes surprising performance of the practical algorithms, the natural question is, can we prove lower bounds, at least for these class of algorithms? Unconditional lower bounds. And actually, there are no lower bounds for a graph coloring problem, and that is for worst case graphs. By worst case, I mean these hardness results are established to be a reduction from other lower bounds, from other problems where we know lower bounds. Then the drawback of these results is that the coloring instances, the graphs you create from those in production, is somewhat artificial. And actually, leaves open one important problem: is it possible that coloring is easy actually on most of them, except those special worst case graphs? And to answer this question, actually to rule out this possibility, what we look for is the so-called average case hardness results. One example of such results for a slightly weaker class of algorithms called CDCL solvers were established in this paper about 20 years ago. It says that if you draw a random graph and then feed your graph to the CDCL solvers, then with almost probability 1, these solvers require exponential running time to tell whether this graph is k-colorable, as long as k is greater than 2. If k is 2, then it's.
Can I ask about this? Seems very unusual to say, like, if you really are like Erdős-Rényi and you take k equals 3, then it's like if you have a forklift, you probably will have like a forklift there.
That's a very good question. So these random graphs are sparse random.
Okay.
With high probability, there is no such forklift.
Okay, so it's really the number of edges is like about
constant.
Yeah.
Sorry, average degree is constant.
Oh, yeah. Okay. Then next, what was it? Yeah.
And here's our result. We show that actually for Gröbner based algorithms or Hilbert Nullstellensatz, basically the same result. And the high-level approach we establish such a result is the proof complexity. And here is usually how it works. So we first formalize how these classes of algorithms, how they reason about a problem. They agree. And we formalize the way they reason as a proof system, which is a formal system. And then naturally we show that the fast execution of such algorithm will yield a very short proof of the fact that the input graph is colorable or not. And then we show that there can be no such proof at all in the first place. So any algorithm must run for a very long time. Okay, so to talk about these proofs, the graph coloring these proofs, we need to know the encoding. Here is the general encoding. You encode our problems as a set of polynomials, say P1 through Pn, about variables x1 through xn, say. And the problem has a solution if and only if these polynomials have a common root. And to refute that there is a solution, you search for such a algebraic line demonstrating that actually there is no common root. What I'm saying is that if you have such a line, then you cannot have the common root, because if you plug in, the left-hand side becomes 0, but the right-hand side stays 1. So it's a proof of no common roots. And in fact, if your variables x are Boolean, then this is a complete proof system, meaning that if there is no common root, then there exists such a line. Now, polynomial calculus is a more dynamic version of the previous proof system. Namely, now we're given a set of input polynomials called axioms, and we derive new polynomials step by step using one of the two rules, non-deterministically. So you get linear combination any p and q that you have derived, meaning that if p is 0 and q is 0, then any alpha p plus beta q is 0. And then you can do multiplication. If you have derived p is 0, then of course x times p is 0. And the goal is to use this rule and then finally produce the polynomial 1. And we measure such a proof by the number of monomials in it. A slight technical thing here is that we also allow dual variables for this proof system to be somewhat strong. And the proof degree is measured by the largest degree of any proof line. Okay, so that's the proof system we care about. And now the encoding of the p-coloring problem. The variables are x, vi for every vertex v and color I. It indicates whether vertex v gets color I. And once you draw a random graph, you fix the graph, and then write down the axiom polynomials as follows. And actually, these are some types of polynomials. The first one says that each vertex gets a color. So for each fixed vertex v, the sum of the colors is 1. And for different colors, their multiplication must be 0. And there is no monochromatic edge, meaning that if UV is an edge in G, they should receive different results. And finally, says that Boolean axiom says that the variables. So clearly, if such a polynomial system has a common root, then the graph is k-color, and vice versa. Before we move on, I want to mention that there are other ways to encode the graph coloring problems. It's via the use of this multi-valued variable xv, h mod v, and it takes value in the kth roots of unity. But if you care about proof degree, there is at most degree k substitution between these two sets of variables. So proof degree will now be affected by a modulo vector of k. If you have proof degree d proof in one system, you get at most kd in another. And here is formally the formal statement of the theorem. if G is a random sparse random graph, or if it is a random sparse graph, then with high probability, every polynomial calculus proof of the fact that G is not recoverable must have exponential steps. And here the subtlety is that I said it's a fact, because if G is a random sparse graph, then with high probability, indeed the graph is not recoverable. So we're not trying to prove something that is wrong. And this result holds for any field, and it holds for both random regular graphs and random. And as you might have guessed from the way I talked about it, we actually care about proof degree. That is because if we can prove omega n degree lower bound, then there are standard ways to get an exponential size lower bound. So in the rest of the talk, we will concentrate on establishing a degree lower. By the way, if you have any questions, just sorry, repeating stuff. So our task, in other words, is to separate the polynomial 1 from the set of polynomials that are derivable from the axioms in degree t. And actually, we're trying to separate one point, to view all the polynomials as points, from a linear space of other points. And therefore, it's very natural to think of the dual language. And actually, it suffices to find a linear operator R, a linear map, from the space of polynomials to the field itself, such that it maps axioms to 0. And as long as it maps some polynomial to 0, you are guaranteed that it maps variable times that polynomial to 0, provided that the polynomial itself is low degree. And then we want that this operator maps 1 to be non-zero. Why do we want these properties? It's because if you have these three, then assuming you have a low degree proof, degree D polynomial calculus proof, then starting from the first line and continuing line by line, you will see that this R maps every line on the proof to 0. However, this R mapped 1 to non-zero, so the polynomial 1 cannot be in your proof. In other words, it cannot derive polynomial, showing that there is no such low degree proof. And here is a nice picture. Well, don't ask me what this shape means. It says that if we want to show that every polynomial that is in degree D and derivable doesn't include 1, we create an operator R whose kernel contains these polynomials, but not contains 1. And now to construct such a map, we need some tool. And that is from the polynomial ideal reductions, mostly in the Gröbner basis literature. So here's the basic setup. We assume that we have a total order on the set of polynomials we care about, such that 1 is the smallest, and they satisfy some natural properties, like if M is a submonomial of another monomial M, then the submonomial will be smaller. And then recall that given any set of this fancy P, the ideal generated by means all possible linear combination. Actually, here means fx linear combination of elements from the polynomial set. Just a notion. And of key importance is this reduction operator. A reduction by actually the ideal generated by a set of polynomials is a linear map from the space of both polynomials to itself, such that given an arbitrary polynomial Q, the way you think of this operator is that you try to pick some elements from the ideal so that you can use that element to cancel with Q to make Q smaller. You can think of it as trying to cancel the leading monomial of Q, meaning the largest monomial in Q, and then do this repeatedly. If you cannot cancel the leading one, can you cancel the second one, and so on and so forth. It turns out that this operator is linear. It is well defined. Its kernel exactly the ideal, and it's actually a projection, meaning that it's eigenfunctions. Here's a very short, simple example. If this is your polynomial ring from any field F with two variables, and we have an ideal generated by one polynomial x plus one, then this operator, and we order the variable to be x greater than y and extend it lexicographically to all monomials. That's a setting. And this operator, reduction by the ideal of x plus y, it simply maps every monomial of the form x to the a, y to the b, by substitute to a monomial by substituting x to b minus. Special case, that's first. And linearly extended to all polynomials. Now we have this reduction modulo and ideal operator, which is good, but it's not sufficient because using this operator alone wouldn't give you any lower bound. The reason is that as long as your input axiom is indeed unsatisfiable, then the polynomial 1 is always inside ideally generated. So if you apply this operator to all polynomials, it kills everything. You cannot get an operator that maps 1 to be something non-zero. And one important idea here is that we can do some refinement of this. We can do some refinement by doing reductions, not modulo the full set of axioms, but in the following way. So given a monomial M, we want to reduce it, but only by modulo an ideal that is generated by a subset of the X. And such a subset, on a high level, vaguely speaking, consists of axioms that closely discuss the variables appear in your life. We will see more explicitly in the coloring problem what this means. But anyway, if we decide such a, if we do reductions on this monomial-based manner, then we can call the resulting linear extension operator a pseudo reduction operator. And the intuition is that we want our reduction to behave like an ideal reduction, especially on low-degree monomials. However, we don't want to kill one. Let's see where we can go with this idea. So here are some concrete properties we want out of the pseudo reduction operator R. Closely mimic the previous three properties you have seen. So we want a map any axiom to 0, and we want it to behave somewhat nicely with respect to multiplication rule, and it doesn't kill one. So following the similar logic as before, if you have 1 and 2, then you can show that each proof line in a low-degree proof will be killed by R, meaning that it maps to 0 by R. But the third one says that 1 is not. So 1 is not the variable. And for the graph coloring, the way we construct such a pseudo reduction R is that first, to each monomial, we will assign a vertex, let's call it V sub M. That vertex, vertex set, no vertex. And that vertex set decides how we reduce monomials. Given a polynomial that looks like this, a linear combination of monomials, we first by linearity, we rewrite that. And for each monomial M, the pseudo operator R acts on M by a true ideal reduction, but only modulo the coloring axioms on this vertex set. So that's the idea. Given a monomial, you identify the vertex set, and you reduce that monomial by the coloring problem, saying that that vertex, the induced graph on that vertex set is capable. And of course, as you can see, the main technical work is that we need to define this VM and then show the resulting operator indeed satisfy these three. Now let's try to define it. So first of all, very naturally, given a monomial in a coloring problem, we mention some set of vertices. Right? For example, if monomial is a degree 2, says, oh, that's it. I'm sorry. XB11 and XB43, then it mentions two vertices. It says vertex 1 color 1, vertex 4 color 3. mentions vertices V1 and V4. And the way we define the desired vertex set associated with M is the following. We first define a notion of a closure of an arbitrary vertex set, denoted by closure of U, and then let the desired vertex set associated with M simply to be the closure of the vertices mentioned. There is a bit of chain of the construction. We will see some pictures very soon. Since I call it a closure, it should satisfy some natural properties. The first two are rather standard. The first one says that if you given a vertex set U, we define as closure U. We want this closure, of course, to contain U and to be in some sense inclusive, meaning that if you pick any vertex subset from the closure, you take the closure of that subset, you stay within the original. And we want the closure to be not too large, meaning that it's kind of a low operator. If you start with a small vertex set, you end up with a somewhat small. And finally, somewhat mysteriously, and I will explain it to you in detail, is this so-called reduction closed property. It means the following. You start with a monomial M, okay? And then you think of how the closure, the reduction operator by the ideal of the coloring problem of the closure on M, what does it do to M? And then you think of, okay, if I enlarge my closure by another small vertex set, and think of the coloring problem of the slightly enlarged subset of induced graph, you want to achieve the fact that the reduction doesn't change. Let me zoom in to see what this means. Maybe a graph is more helpful. Assuming that we have built a closure of vertex set U, this is a closure of it, and we have colored the induced subgraph using, let's say, 3 colors. And now someone else gives us another subset of vertices J, and we are now have to consider the vertex subset closure of U union with J, and think of the graph coloring problem on that slightly larger subset. Then, to achieve that reduction closed operator, semantically, you can think of that our task is to, or not words, it suffices to achieve the following. Given any K coloring of the closure, you can extend it to the slightly enlarged subset to be a valid coloring of the slightly larger induced subgraph. That's the minimum condition. And actually, not only we want that, assume that we order the vertices from the beginning, say 1, 2, 3, in any way. We want to achieve this coloring extension in under a technical condition that is called, or we can call it order decreasing, which means that, okay, you're given the coloring of the closure, and now we are to decide the coloring of each vertices in J minus closure of U. We want to do it in such a way that when deciding the color of a vertex, say V there, we only look at the vertices inside the closure that are smaller than V. We have to make our decision on the color of this vertex by only looking solely based on the information, but not on the vertices. And we want to achieve the fact that after we do it to every individual V, the resulting thing will be a valid color. So that is semantically what we should do. In graph theoretic terms, to achieve such a thing, it turns out it suffices to prevent certain kind of structures outside of the closure. These are graphs, and let me provide some caption of the graphs or explanation. The first one says that you shouldn't have a vertex that is outside the closure and is adjacent to something inside the closure, and that vertex is greater than the vertex you started with. Remember, we assign a total vertex order from the beginning to the scheme. That is the first kind of thing you should apply. The second kind of thing, it says that, okay, there are two vertices. Both of them are adjacent to something inside the closure, and there is some correlation between, namely there is an edge. We don't like it. And the third one says that there is some vertex that has more than one neighbor inside the closure, regardless of the relative order of these vertices compared to one. So these are the three types of structures we want to prevent if we want to achieve that order decreasing color extension. And I must mention that these are actually exactly the same structures as identified in this Romero-Tantra work in the context of large group growth. So it's clear for us that what we want to prevent in the complement of closure, and therefore we can design closure to minimally satisfy these conditions. Namely, what we do, we are given a vertex set U. To build its closure, we repeatedly do the following. First of all, we take all the vertices in G that can be reached from the current sets via an order decreasing paths. This is to prevent the first kind of thing. If you include something in U, you should include all these descendant vertices in U in your closure. And then once you have done that, if you see a type 2 or 3 structure outside of the closure, you add them to your closure. And you do these two steps repeatedly to eliminate all possible 1, 2, 3 structures. And when your current set doesn't enlarge anymore, you take it to be the closure. Very good, very functionally defined. And actually, it's not hard to show that at least this definition is well defined. And then our task again is to recall what we need out of the closure. I think the most significant, technically significant part is that we want to control the size of the closure. If you start out with a small vertex set, roughly speaking, 2 to the d to the omega 1 times n. Here, d you can think of as maximum vertex degree, 10 or 15 fixed from your random graph model. Random regular graph model. If you start with a random graph, there is some issue with maximum degree. I want to focus on that. Then we want to show that its closure is not large. Basically, after we show this, then the proof will write itself, and that will remind you at the end. But as for now, let's see how we prove. So again, let me remind you that we start with we assume a vertex order in the beginning when we talk about its color extension, etc. And this property, the size lemma of the closures, it relies on really using the proper vertex ordering. And this vertex order is introduced. In hindsight, it's actually very simple, but who knows how we come up with this. So we order the vertices of the graph according to any true coloring of it. And if you think of a random graph of, say, average 3D, then it's with hyperbolic, it's not recolorable, but certainly it is decolorable, assuming the maximum degree is d. And d is a constant in our case. Think of it as a 10. And the effect I want to achieve via such a coloring can be shown on the following picture. So, assuming the graph G is given, and we color it according to a true coloring of it, then these are the color groups. And then every graph edge is between different groups. And we order the vertices in any way that respects these color groups. Let's say 1 come first, and then 1. I don't care about inside the coloring group how we order. The crucial property that this coloring or this vertex order gives you is that if you look at the picture, any order decreasing path, it necessarily has length at most, say if you use C many colors, It has length at most c-1 because there is no edge in each of them. And you cannot go back and forth. You have to go to the right direction. And using this crucial property, we can show that the closure is not large. And here is the intuition on loneliness. Like when we start building this closure, we build it in rounds. Each round, we need a new round because we detect a type 2 or type 3 structure. And the thing is that once you have such a structure, it will reveal actually a sequence of vertex subsets inside the sets that you're constructing, the U1, U2, And because of the type 2 or type 3 added, each time you add at least one more edge than a vertex in this sequence of subsets, and therefore the graph edge density of them will be strictly increasing. And here, by graph edge density, I mean the number of edges within this set divided by the number of vertices within it. If your construction goes on, then there is a sequence of subsets with a larger and larger edge density. However, there is an analytic property of the random graph saying that random graphs has actually 1 plus epsilon edge density everywhere for small vertex sets, where you can think of epsilon as little 1. And therefore, you cannot have too many rounds a priori because that will boost edge density above the random graph edge density. And each round increase the vertex set size, but at most the d to the ig, sorry for the typo, is because you take all the descendant vertices that are reachable from the current set by edge order decreasing path. But the underlying message is that this is a constant. Don't run large. Okay. So that's basically how we control the closure size. And now recall that. Now we need to check that the closure gives what we want, the 3 properties. Given a closure, we know how to assign a vertex set assigned to any monomial vertex set. And we define a pseudo operator R to be the true ideal induction of that extended module with that coloring problem of that vertex set. And now we check that in this definition, R of each axiom will indeed be 0. And roughly speaking, that's because every axiom P in the coloring problem, it mentions at most 2 vertices. Either it says the vertex one vertex gets one of the colors, or it says 2 vertices cannot get the same color. And so the closure of the vertices mentioned actually is small. And therefore, by the property of closure being reduction close, actually we can show that the way our pseudo operator reduce every monomial M inside the polynomial P is by the same reduction closure. By the same reduction operator. And if you have this from writing some algebraic stuff, you will see itself that this thing reduces the polynomial P to 0, because P is part of that dimensional. And similarly, we can show the second property. That's if you have a line, if you multiply the polynomial by x, then do the reduction. It's the same as you do the reduction to the polynomial, multiply the result by x, and then do the reduction. I think if you're interested in this part, I can demonstrate it in the second part of the talk. It's a bit painful if I try to describe the procedures for this more mechanical procedure. And at the end, the pseudo operator will map 1 to 1, actually, meaning that it does nothing to the monomial 1. This is because the monomial mentions empty set of vertices. By our definition, the closure of empty set doesn't do any reduction. And therefore, these two properties show that every proof line is mapped to 0, low degree proof line is mapped to 0, or a line shows that no, 1 is not. And that gives a result. In summary, we show that polynomial calculus requires exponential lower bound for coloring problems on the blocks. And it implies exponential running time for the corresponding algebra. And some open problems that I'll mention. So we deal with other algorithm classes. There are other prominent algorithm classes, especially let's say Schneider's, sum of squares. What kind of hardness, especially average hardness, you can say about the graph coloring, either in terms of size or in terms of, I don't know, some refined hardness to control the width of the proof, how delta size, how delta size. There are many questions that you can ask about them. And the second one is that if you change the problem, coloring actually you can view it as a special case of CSP problem. How about written CSP problem for one? And the third one is about the technical. Is on the technical side. So our proof, actually, if you look at it carefully, is kind of different from the previous polynomial calculus and lower bounds proofs. We don't know, at least so far, we don't know how to unify the current and the previous polynomial calculus and lower bound proofs. But perhaps there is some refining, unifying framework behind. And thank you. That's it.
Any questions? So what do you think about Shirley-Adams and sums of squares? Do you think that anything like this, I mean, are we looking to strengthen this framework a little bit, or proofs are going to go in some kind of completely different way? Or?
Well, Bartolomew's random proof will be going in a very different way. And I think the realistic chances of getting a degree will show. And for Shirley-Adams, I think it's more interesting to care about coefficient size.
So can you extract some graph property, let's say like property P, and say that whenever a graph has this property, then you need exponential proofs, or is this very difficult to define such a property?
Everywhere sparseness. That's the pseudo-random property where. Meaning that if you take any subset of vertices of degree, let's say n over 1000, the number of edges divided by the number of vertices restricted to that subset is bounded to say 1 plus epsilon, where epsilon is a proper small cost.
But you do have like 3 colorable graphs that are everywhere sparse, right?
3 colorable graphs that are very sparse, of course.
But this. Then should you be able to prove that even if it's 3 colorable, the proofs?
Then the proofs of 3 non-colorability are very, very low.
Oh yeah,
it's extremely hard to prove that they're non.
Yeah, okay, yes, I see. So it somehow it doesn't talk about the ESP. It doesn't say anything about the ESP instances. Okay, yeah. So it's like ESP instances. We just ignore them. I see.
Mm-hmm.
But from this everywhere sparse, I haven't thought about this. We also need that the chromatic number is somewhat low, right? Is that's independent of this, or?
I think there is some numerical. We need to go into the numerics to see. I mean, because if it is everywhere sparse, you can partition the graph into constant many number parts and then color each of them using 3 colors. But I think this will create some numerical problem. So I would add the second property as you can color it using some, say, constant number of colors. The graph, chromatic number of the graph is upper bounded by an absolute constant. Depending on the degree.
Any other questions? Questions from the virtual audience?
Well, maybe the question from someone with a little more practical look on things. Like, do you actually see this in practice for these algorithms, or are they simply doing some pre-processing or something that's not covered by our approach?
Maybe that's, I don't know if we should ask George about it. My limited understanding would be that applied algorithms would perform very poorly for random graphs if you don't care about random graphs. It's like an interesting input, but it's an hard input.
Yeah, if you have large graphs, usually they are sparse, but they require many colors. So there is a sort of a small core that is not sparse and gives you the lower bound of the chromatic number. So you don't have this property.
Another way of saying that, if I give you a random graph, there is no such core.
Yeah, probably.
I mean, and in particular, I guess you can say, I mean, so the Shuo flashed some references for successful algebraic algorithms, and it stands to reason then that well, in particular, they were not run on these types of instances, right? Because then they wouldn't have seen this good behavior, because those algorithms are captured by polynomial calculus.
Yeah, so the question is like, so maybe they're doing algebraic reasoning plus some type of pre-processing, somehow this pre-processing doesn't fall under the proof, and that's
We need to check the reference.
No, I think my understanding is that they just perform poorly on these types of graphs.
Okay.
So, in the same way, like also, I mean, this is similar to other problems. There are amazing max-clique algorithms, but and then what you do, you run these max-clique algorithms on Erdős-Rényi random graphs, and they perform very poorly. Do you want to say anything? So we'll have a break now, and then there's the offer of doing some of the technicalities on the board. Like what's the menu? What kind of teaser can you offer us to,
Oh yeah, sure.
convince us to come back?
Maybe you want to see some of this proof of this reduction lemma, which says why it suffices to have this color extension property to show this closure property we want, and why the closure property would give you the three properties of R operator. I call it a kind of mechanical proof. It's kind of a topological proof, but it's interesting to see it if you haven't seen it. And also, you probably want to see something about this size lemma. And here I will tell you how we use everywhere sparseness of the random graph to establish these things. If that doesn't sound sufficiently attractive to you, then you should let me know what you want to know.
So I think this sounds fair enough, but I would suggest that we thank Shuo again. And then we'll take a break. So we're back again after the break. We have switched to whiteboard mode, and the video camera is getting suitably confused already, so it will probably zoom in and out, but we hope most of the time we will have a sharp focus. Definitely we'll have a sharply focused speaker who will tell us about the details of the polynomial calculus rollout.
Thank you. So I think I better start with reminding you this pseudo reduction operator, what they are, what we want them to do. So I will start with, given the coloring problem, if n is a monomial, then we can say the vertices that M talks about we denote it by, say, these vert sub M. Vertices directly mentioned in M. Okay, and we will define a notion of closure on vertex sets. And denoted by CL. For every vertex set U, its closure is some superset of it. And in this way, we can design a pseudo reduction operator. From polynomials to polynomials. And see here as the following. I will use the letter little ti to make a term, which means a field constant multiplied by a monomial. Sorry, I think I'd better be explicit here. Suppose Ci times monomial I. I define it linearly. I define my operator as linearly acting on each monomial, each term. And on each term, I define it to be the true reduction operator by the coloring ideal generated by the coloring problem on the closure. A bit of involved definition, but that's how we define pseudo reduction operator, assuming we know what is a closure. And now let me put it there what we want out of this pseudo reduction operator. One R1, sorry, R axiom to be non-zero. Sorry, to be zero. Second, we want our XP to be our XRP for any degree, small degree polynomial, where capital D is a degree parameter set from the beginning and set it to be n over a very, very large. Third one is that we want R1. So I give you a definition of a pseudo reduction operator and I give you the wanted properties of that. The mathematical meat of proving those properties actually finally boils down to what properties of this closure should satisfy. Because after all, this is the only thing we don't know in the definition of R. Or actually, this is the only thing that decides, determines the definition of, determines the pseudo reduction operator R.
And you said this during the first half, Shuo, right? But it's worth repeating that if suppose that P would be a satisfiable set of polynomials, then you would set R to be just the reduction modulo these polynomials, and everything that maps to the kernel would be everything that is implied. So since it's satisfiable, like all the axioms and everything that you can derive from the axioms, it will all map to 0. But since it's not contradictory, 1 is not implied, and everybody will be happy. Now, the problem we have now is that unfortunately the graph is not 3-colorable. So actually, if we take all the polynomials, they do imply 1, why 1 does live in the ideal. But now you're going to define some kind of sneaky pseudo reduction operator that looks like you're actually reducing modulo all the polynomials, but you're not.
That is, thank you for the supplementary explanation. That is a high-level idea behind this whole thing. And to further supplement what has been said, let's see, Y property 1 and 2 imply that every line in your assumed, in every imagined low-degree proof would be mapped to 0 by this R if it satisfies those properties. So if P, so starting from the proof, if you apply this rule, then P and Q must be an axiom. And because R of axiom is 0 and R is linear operator in its definition, any linear combination of P and Q will be 0. So R map those lines to 0, so it will map this one to 0. For the second rule, assuming these are two proof lines in your proof, then a priori P should have degree no more than D minus 1 because this thing appears in our proof and is degree bounded by D. And we know by induction that RP is 0. Then let's look at R of XP. By rule number 2, that's our property number 2. We have this is R times XRP. And by induction, we know this is 0. And because R is a linear operator, not only phi is linear, it maps 0 to 0. So at least now you know these three properties make sense. That's what we're shooting after. Okay. And then now we can switch to the closure side. What kind of properties of closure, or why the properties I wrote in the slides of the closure can imply those properties of R via this definition. So given the vertex set U, let's say U is the vertices mentioned in the monomial M. There are some vertices in it. The idea behind the closure is that we find a subset of U such that if you want to reduce any other monomial M prime, let's say, whose mentioned vertices live inside closure of U, then with respect to the coloring problem, enlarging the axioms you care about won't change the true ideal reduction of that monomial M prime. So this is J further contains the closure of U, J small. Question is if M prime is a monomial such that its vertices inside closure of U, is it true that our reduction closure view of M prime is already the same as R of J of M prime. This is a key question. You can think of doing reduction vaguely as what the proof system can reason or what they can do about a monomial. So this property or this question is saying that is closure really sufficient closed in the sense that for any monomial that lives within the closure, your system, all the reasoning your system can do about that monomial is actually sufficiently representative in the sense that even if you throw in slightly one more axioms, your system cannot reason more. It cannot efficiently make use of those additional information. So that is why I think it's called a closure in some sense, at least the way I understand it. It's reasoning closed. And let's see why this property would imply properties we want. This is property number 1, actually. Property number 2 is that, of course, we want the closure itself not to be large. Why? Can you see a trivial design of the closure that definitely satisfies this?
This is set itself.
I think this is not sufficient. Another extreme.
The whole graph.
Yes. If you take your closure to be whole graph, then there is no additional action you can throw in at all. Definitely, it represents the strongest reasoning proof system can do whatsoever. But what is the problem with that? If I did yes, then the pseudo reduction defined out of using that closure will be the true ideal reduction using the whole set of axioms. And we encounter the old and familiar problem that one is not so connected. It doesn't give us anything. So the point of this proof is to kind of design a proper but sufficiently closed. Want this?
Actually, you could be slightly more refined on that. You could say that, well, it wouldn't necessarily show that 1 maps to 1 because 1 could have a different closure. So, maybe you have, 1 is fine. It has a small closure, but then you have some other monomial that has a gigantic closure.
Then this property will be falsified.
But then you're sort of, basically any monomial, if your lower bound is successful, it will show you that you can never derive a monomial with a dangerously large closure, right? That's the way. Yeah, I don't know if this is.
Yeah, maybe it's a way to characterize what monomials are doing.
Yeah.
Are reducible and also. So this is property 1 that we want. And property 2, as I just said, or as implied by our conversation, sort of, is that we want closure to be small. It's bounded by, let's say, all of it. It's not necessarily to say that it's all of you can have something like u squared or whatsoever, but that will decrease the quality of your lower bound. But morally speaking, we want it to be somewhat bounded by the size of u. Okay, closure of that P1 and P2.
Why is it decreasing? You just need to use the sign, right?
Yeah, I mean, the set U comes from the degree of the size of set U is directly related to the degree of your monomial in a group. If you say, oh, closure of U, the size is bounded by, say, degree square, then you are sort of saying that you can only prove degree lower bound at the square root of it, because you want the closure to be.
Yeah, but it's not like you have a dependence on the size of U in the degree. It's just saying if I go over that, I have something that may be unsatisfiable. Right?
I think so far there is no.
Like the time dependency doesn't appear in the comes from some graphs, it comes from the relative. If I have a monomial for which I inflated size too much, I may have something that becomes insatisfiable.
Yes, that's what I mean. To be satisfied was the minimum requirement. There might be more, but that is definitely something we should hold. And this is one way to guarantee that. At the end of the day, we care not only about the closure of one set, we care about the closure of every small set, and we want them together to be well behaving under property number one. So we have to start with somewhere. Let's put a size band on all. Okay, so that is the two unusual properties of closure. But what when I say unusual, there are some usual properties you would imagine out of the name closure of the set. What are they? Actually, if you look at Wikipedia, there is a definition of closure on any post set, satisfying two properties. And actually, those two properties are the usual properties we expect here as well. Okay. First of all, U is a subset of closure. Second of all, the closure is monotone. And actually, there is a third. Closure is idempotent. If you take again closure, if you take closure and then take closure again, you should end up with the same closure. I think in the slides I use the word inclusive and summarize the two last properties as for any subset U prime that is inside the closure of U, the closure of U prime is inside the closure of U. They are equivalent to these. For explicitness, just put it there. So, okay, a bit of abstract play with the notion of closure. And what we want eventually is to say that P1, P2, P0 implies 1, 2, 3.
Returning to Yasin's question, it's like a good question, like why would you want the closure not to be too large? I guess, is it because ultimately we will only be able to deal with linearly large closure sets, right? Which is sort of, and then if like a polynomial of degree D could lead to a closure of, say, size D squared, then that sort of tells me that I would only be able to prove square root n lower bounds on the grid, right? So it's,
if you had a different way of building closure, we could make, theoretically, it could be able to get rid of the size. Then I managed to map monomials to some closure that there is no direction to take. Or I could get a larger sub problem, my coding problem, that's just the size.
Satisfiability, as I said, is a minimal condition, and actually these three properties are sufficient to derive a lower bound.
Yeah.
Actually,
what do you need else from the size level?
From the size level.
Yes. What do you want to close?
I want to prove a reduction level.
Yes.
And satisfiability is part of the reduction lemma, but the reduction lemma requires slightly more than that.
Yeah, the order.
Yes, yes.
But where does size come into play?
In that proof, we need to first color part of the vertices that are not in the neighbor of the closure, and for that part, you require satisfiability. Yes, and you also need to show that once you color that, you can still do the reduction, the variable substitution on the neighbor of the closure, and there is some technical detail there. I'm not sure how general this can be framed, but it might be worth thinking.
it's an interesting question.
Mm-hmm. again, we count myself, what I'm saying is in the proof of property one, about the proof of property one. There you use the small size condition. So apparently now we have two choices. One is to see how these properties imply properties of R we want, and hence the degree lower bound. That is one choice. Another choice is to see how our graph theoretic term defining the closure can imply properties at 1 and 2. So if you're interested in the abstract framework to see how it operates, then probably we can do one, option number 1. Or if you're interested more in the combinatorics, then maybe we can do option 2. Our choice.
Maybe to see how the properties follow.
Cool. So we'll read the definition of R there. Erase these. Oops. One will show R of axiom equals to 0. So axioms have, basically speaking, 3 types, but actually P is an axiom if it has the following form: sigma I from 1 to k, vertex B has to have a color, and for any I that is not equal to I prime, it cannot have 2 colors. And third one is that for every UP that is in H, should have different colors. In either case, the number of vertices mentioned by P, let's define it to be set U. Then we have its size levels 2. So R of P is, let's say, R of, with all loss of generality, let's assume it's T1 plus T2 plus plus TL, where L is either K plus 1 if it's of type 1, P is of type 1, or L is actually 1 if it is of type 2 and by definition, this is sigma I, R of closure of Ti. By definition of once we have a notion of closure, we define it in that way. And it's written there. And now look at this. By property number 1, for each of this, I can enlarge this set a little bit to be the closure of U. Maybe P1 and P0. The reason is from P0 we can show from the fact that the vertex mentioned by Ti is of course in U, because we define U to be all vertices the axiom can mention, in particular this term can mention. You can show that the monotone property follows. And on the other hand, by P2, P1 and P2, I should really say we use all the properties. P1 and P2. We know that this closure of U is small, and hence reduction modulo closure of Ti is really the same as reduction of closure of U of Ti. Because this set is slightly larger, actually it includes that other person, and it might be slightly larger, but the whole size of that is controlled. So by the being reduction close, we know that if you enlarge your closure by something that's slightly larger, the reduction doesn't change. Cool. And then we got from this line, we can, because now we are doing the same true ideal reduction for the same ideal, we can plug the summation back in. And this is P. And by definition, P itself is the axiom, one of the coloring axiom that only talks about vertices in closure of U. So in other words, this very polynomial you're trying to reduce is in your ideal, which by definition gives you.
Got a little bit confused. Is this different from, I was expecting you take your axiom, you're not sure what the closure is, but you can definitely add to it the vertices in the axiom, because that's only like 2 more vertices. So that doesn't grow. And then J would be whatever the closure is, which you don't know, plus the maximum 2 vertices mentioned by the axiom. And now you just use property 1.
The thing is that for different Ti, you have different J's. You need a dominating thing for all those J's.
Well, we're looking at the axiom. The first axiom only mentions 1 vertex.
Yes.
And the second axiom only mentions 2.
And third one too as well.
Only mentions 2. So I think this is like.
I'm doing it a bit to maybe overgeneralize the way it works. Okay, back to axiom also mentioned.
It wasn't clear to me how you knew that the closure of Ti was contained in the closure of U.
Oh, it's because we define U to be all the vertices mentioned by polynomial P, which is a union of all the vertices mentioned by Lund.
Yeah.
And in our case, it's still bounded in 1 or 2. And it's by the monotonicity of the property, because each vertex mentioned by Ti by definition is in U.
Okay.
Therefore, their closure is unclosure.
Okay.
So closure of U dominates the closure of everything else. And the basic idea is to replace every different closure I by this dominating common closure of U and right. doing it really over generalizing, because if you look at the actual axioms, you don't have to do it like this.
Yeah, I guess I'm not sure why you need to take the closure of O, because okay, because you want to be yeah, I guess no, I don't.
I want to find a common dominating set that is sufficient to do
Okay.
reduction for all the terms. That's the general
Okay.
condition. Okay, cool. So we have checked R of x is 0. And now we are going to this a bit mysterious looking property number 2. Or perhaps we should do property 3 first. Property 3. On the slide, if you remember, I mentioned that by our combinatorial definition of closure, the closure of empty set is empty set. Therefore, there is no ideal. You reduce, and therefore this operator of monomial 1 does nothing, so you get 1. But actually, you don't need to go to that extreme. Even with the current size bound closure, you can do it, plus the satisfiability. So, what was number 3? One is actually 1. Okay. So vertex is mentioned by 1. Is empty vertex set. In particular, the empty set is size bounded. So by P2, closure of empty set is bounded. Assuming that I don't know how I define closure, but I only have those extra properties of closure. This is all I know. And here I want to say there is an additional input. It says that G restricted to any small vertex set. The is K-colorable. The induced graph is K-colorable. I will use this property, although I didn't write it. This implies that the ideal generated by K-coloring of closure of the set is satisfiable, meaning that they have a common root. So reduction modulo this ideal doesn't kill 1. This is because of soundness of the root system. If your polynomial set has a common root, then it cannot derive 1.
I'm a little bit confused from property 2. Do we actually know that the closure of the empty set has constant size?
No, we only know it's oh, actually, yes. The way I wrote it is bounded by all of you. A looser way you can write it is bounded by some absolute parameter depends only on n, like n divided by 1000. But the way I write it like this simply because we can prove this wrong. And you're right, if I use property P2, then here I know it's a constant size. Although we wouldn't make use of this to improve any part of the proof.
But basically you would say, okay, any small enough subgraph is colorable.
Yes. And at the end of this session, maybe I can show you a small proof of that fact. Now we are moving to property 2, and let's see if I can manage myself on board with that. A bit, but I'll erase property number 1. By the way, just kind of a recursion from what we are doing, but just for your information, if you rearrange terms, knowing that R is a linear operator, this is actually saying that R times X times P minus RP is 0. And if you observe a little bit, you will see that the way we define the pseudo reduction operator also satisfies that it's idempotent, it's a projection, which means this is precisely, if you take all P in the domain of R, then P minus RP, everything like that, you take it, they span the kernel of R. This is satisfied for every idempotent linear operator. So property number 2 is precisely saying that, assuming your pseudo reduction operator is a projection, then its kernel is closed under low degree multiplication. We will not make use of this fact, but just, I think it's nice to know. To ease your mental, sorry, never mind, to ease your mental difficulty with this abstract nonsense. Okay, and now I'll erase it. I'll demonstrate the correctness of this property. So, assume, again, our reduction operator is defined term-wise or monomial-wise, so we expand everything down to Ti, where Ti means a term, a constant times monomial, and I will later on will write closure of Ti to mean the same thing as the closure of the monomial in Ti. Now let's see. Let's start with the right-hand side because it's more open up. Let's assume, and we need an expression of this RP. It's defined term-wise, so let's assume our Ti further as J, Tij for some new terms. Then observation, the vertices mentioned by each Tij is a subset of the closure of Ti. This is by property 0. How do we see that? So how does a term come out of the reduction procedure of Ti? It means that you use Tij plus something else to be Ti plus some linear combination of Pi, Q, I, let me use QL, where PL is in the ideal generated by the closure.
Can I nag you a little bit again?
Yep.
I'm getting a little bit confused. Like in particular, if we want property 2 to hold, it has to hold also for single terms, right?
Yes.
And if it does hold for single terms, then we don't need to look at the polynomials.
Not quite, I would say. I don't see why.
Why?
The reason is that
Because then we just argue by linearity. So I would just prove this for monomials and be done. Or terms and be done. Because we know R is linear.
we know R is linear, then we know the left hand side is linear operator. For the right hand side, probably all right.
I mean, I'm doing it in 2 steps. First, I say, because you could say like, it looks like.
Let me use M1 and M2, assuming I have established what you said on monomials or terms.
No, I'm just saying, the first thing I do is just set P to be a term.
Yep.
And then it definitely has to hold.
Yes. Assuming I have established this line precisely what you said from here to there. Then I have R times X times RM1 plus RM2. And this is R times a linearity again, R of M1 plus M2. Yeah, all right. Thank you for simplifying all this then. I only need to, with all of the generality, assume P is a single monomial. The reason is shown here. If we show that this property holds for every monomial I, and we know R is linear, then it, using the property, this is shown for monomials. And then I use linearity again to plug them together and get back to what I want. Thank you. So let me clean up the board a little bit and start on there. Step number 1. For P is a single term, T. Step 2. Extend to P is sigma I, and by this law. Well, we carry on step 1. So again, assume, I think I'm writing basically the same message, but in simplified terms now. RT.
In simplified terms, no pun intended.
Yes. TI. Then the first observation we have is that observation by property P0 is that the closure of each TI is contained in the closure of T. And the reason is, as I explained, how do you get Ti out of T? It's because you add something, some polynomial, some ideal, some element in the ideal generated by the axioms talking about those vertices to the T. Ti plus some lower terms. is T plus some sigma I, Pi, Qi, where all the variables in Pi are in the coloring. Okay, I'm being a bit sloppy here. I'll use the closure of T. The coloring problem on the closure of T, I just want to state it.
Sorry, can you explain this again? I lost you. So why do we know? So we reduced T and we get some of Ti's. I agree that definitely closure of T, that would be a good thing to have. But why is it by P0 again?
Yeah, no, I'm trying to show it now.
Oh, you're trying to tell me.
Yes. The reason is that how do I get the Ti? No. Let me write it this way. Sigma I Ti is the result of adding something in the ideal to T. Now, we know that we can set all variables that is outside of the closure of T that mentions vertices. So each variable has a unique associated vertex, of course. And I will set all the variables mentioning vertices that is not in the closure of T to 0. I do that to this line. So I will get Ti prime is T. T is unaffected because T is unaffected. Because by definition, T is containing vertices mentioned by T is containing closure of T.
So you don't want the ideal bracket 0. You're actually looking at the polynomial, right? But like Pi don't live in the ideal. They actually live in the closure set.
It is a member in the ideal. The coloring ideal. Oh, I think, yes, it's more, let me write this way. Axiom on
Closure.
of T.
Yeah.
Their product is in the ideal. Thank you.
Yes.
Now, having such a line, I first do some operations with it. I just set all irrelevant variables to 0. But irrelevant, I mean they're mentioning vertices outside of my closure. The crucial effect is that T will not be affected if I apply this variable assignment to that equation, because T mentions vertices only. And crucially as well, each Pi is not affected because Pi only mentions vertices in closure. Qi prime. Now, two things to observe. First of all, let's call this old equation star. Let's call the new equation star star. Observation number 1. The left-hand side of star star is no more than the left-hand side of star. By no more than, I mean under the partial polynomial order. Actually, they are comparable. It's because here we use the fact that the ordering on the monomials we use, they should respect variable substitution. Namely, if you have a monomial, you set some of the variables in it. Well, actually, since we set variables only to 0, I can only require a weaker condition. So after I do this operation, what is effect on the target? Either it remains intact or it disappears because I set every variable to 0, some of the variable to 0. So trivially, the left-hand side of this star star It is a subset of terms of the left-hand side of star, so it is smaller than that. So by definition of reduction, true reduction of ideal reduction, since we are reducing the same term t, if you get the result out of your reduction, it means that you cannot reduce it further. This is hidden in, or another way of saying that is a reduction operator is an idempotent. That's idempotent. If you have reduced a term to be smaller polynomial, and you apply your reduction operator on a smaller polynomial again, it shouldn't change anything. If it changes something, it means your reduction in the first place is not done yet. So star star has to be equal to star. Again, because t is not changed, the ideal is not changed. That's observation number one. So I can erase this t prime after that. Observation number two. Now we look at the star star. Can you tell me the variable set of the right-hand side? Or at least a superset of all the variables on the right-hand side? Closure of T. Because I set everything else to 0. Therefore, the left-hand side has to mention only variables in closure. And these two together means that the original left-hand side, each term alone could only mention vertices in the closure. So this is a small footnote explanation for.
And now we use property 0 again.
Uh,
So now we know that the vertex set mentioned by MI, the TI is in the closure of T, and now we can take closure on both sides.
and repeating the thing we did for x8. I don't skip writing it. The message is that once you have this, then the reduction operator on each of Ti is exactly the same as doing the true reduction using one set closure of T. This here we use the smallness of closure of T and the reduction close, namely P1 plus P2. And you do some term algebraic manipulation, you can see the terms equal to what we want. So that is the option number one. The explanation for option number one, namely properties of closure implies property of R.
I mean, we're cheating a little bit.
Where?
Because we added I mean, there's an X that you're multiplying with also. So now we argue that for all MI, the reduction operator mod closure of MI, we could reduce mod closure mod M instead. But actually what we want to say, T, sorry. But what we want to say is like that instead of reducing mod the closure of XTI, we can reduce mod
XT, closure.
SXT, but that's just the small, I mean, that's just adding a variable, so it follows from some property again, I guess.
I would say you run this argument again, but when you previously we play with t, now we need to play with x. Well, not exactly like that. I'm pretty sure it's not hard to figure out, but maybe you need to write another application.
I don't remember. Yeah, I don't think it's. I think we're morally there.
Yeah. But similarly, we want this, and that is actually what we. Unfortunately, time's up. The beautiful combinatorics.
Yeah, maybe I chose the bad part for us. Apologies for this. But this sort of tells you, so what did we learn now? That not even, yeah, I guess you did slightly more abstractly than I did if you think about the axioms. But I destroyed that part for you. But if I would have allowed you to be a bit more abstract on the axioms, which you were, you're sort of, these properties P1, P0, P1, P2 are sort of saying that for any collection of polynomials encoding a problem, if there's a notion of like I guess there's a notion of a vertex set somewhere.
Where is it mentioned by now?
Or yeah. Or you know, or yeah. Or variables. I mean, there's a sort of we have actually variables that take integer values, right? So that's what we mean by, we think of xv1, xv2, xv3, xv4. They're all sort of speaking about v. So we have a notion of like actually an integer valued variable. So we're sort of collecting those, and then we're defining closure in terms of those actual non-Boolean variables. And if we can define a closure operator for which these three properties hold, then we can then just plug it into Razborov's definition of a fake pseudo-reduction operator to prove that low-degree derivations will never be able to establish that these sets of polynomials are unsatisfiable because
it has three.
Yeah, because of these properties, which is sort of saying as long as you're in low degree, it actually looks like you're doing an honest reduction, but you're failing, like one doesn't reduce, so clearly you're satisfiable. So I guess. Hey, any other questions or more enlightening comments? Less enlightening comments? Maybe we should thank our speaker one final time.